Hi everybody, it's Mr. Zarzak, and in this video I'm going to talk us through how to think through RC circuits. Okay, an RC circuit is a circuit that has one or more resistors and a capacitor. So let's get to it. All right, we've developed these equations for charging a capacitor. All right, and before we put them to the test, I have kind of two cheats that I like to use, ways to think about the behavior of capacitors. Now, we're going to start with the two cheats, okay, and then we'll talk through why they behave the way they do and what I mean by my two cheats. Okay, so when you see a capacitor in a circuit, when we first close the circuit and turn the circuit on, I want you to think of the capacitor like a wire. Okay, so initially it just acts like a wire. What that means, I'll show you in a second. Okay, and then I've got at time is equal to infinity. Now, we don't have to wait forever, but all I mean by this is after a relatively long period of time, okay, the behavior of the capacitor, okay, it's going to act like an open circuit. All right, what does that mean? Okay. So these are the two equations that we derive for charging a capacitor. One defines the charge on the capacitor at any given point in time. The other is the current through the capacitor at any given point in time. All right, so if we look at this initial condition, I say at time zero, the capacitor acts like a wire. Okay, so then what's that mean? All right, well, if I take and I look, all right, at this formula here, okay, and I try to sub in for time is equal to 0, well, what do I get? All right, so then I get this Q of t is equal to CV, where C is the capacitance, V is the voltage. I can get 1 minus E to the negative T over RC, but, well, if I plug in for when time is equal to 0, all that stuff just goes to 0. Okay, the R value, the T value, the C value, none of that matters, it's all 0. All right, so then what happens is that E to the 0 is just a value of 1, so then I get this Q of T is equal to CV, 1 minus 1. So initially, what this is telling me is that at time is equal to 0, there's absolutely no charge on the capacitor plates. Okay, so what? All right, well, if I look at what's left over here, okay, this is C times V times 0 is equal to 0. Okay, what does that tell me? Well, capacitance is really just a measurement of the charge per voltage, right? We know this from before, and, well, the capacitor itself is a physical device. It's something that we have to manufacture, so we select materials, we select conductors and dielectrics, and we make them different sizes, have different gaps with them. Okay, so it's something that physically that we manufacture that is not dependent upon charge and not dependent upon voltage. So all I mean by that is if I go capacitance times voltage is equal to charge, all right, well, we know at time 0 that initial charge is just 0. Okay, so then if the capacitor, if the C value is just some constant, okay, well, then all that means is that the value of the voltage must also be equal to 0, okay, initially. Well, so what? Well, that voltage is a change in voltage, see? So, like, if we look at a circuit, here's a circuit. Okay, we'll analyze this in a second, but if we move along, okay, a conductive path, remember we used to call those nodes. All right, well, that means that there's no change in voltage. All right, if there's no change in voltage across the capacitor at time is equal to 0, well, then it's just acting like the continuation of a wire. So that's what I mean when I say at time 0, the capacitor acts like a wire. All right. Number 2, at time is equal to infinity, or after a very long time, the capacitor acts like an open. Okay, what do I mean by that? Okay, well, then I'm going to look at this equation here. All right, the current through a capacitor is defined as the voltage times this E to the negative T over RC over R. Okay, so if I write that out, I'm going to put the V over R like that, just so we can focus on the E to the negative T over RC. Okay, well, if I plug in a very big value for the time, okay, and I know it says infinity, but we don't even have to go out to infinity, all right? Just conceptually, what's that mean? Okay, so that's 1 over E to the infinity. Okay, 1 over E to the infinity, that's just 0. So any number times 0 is just itself. So after a long period of time, okay, the current that flows through a capacitor is 0. All right, if there's no current flowing through a circuit, okay, it's like taking a light switch and turning it off. You open the circuit. Okay, when we say it acts like an open, means no current is flowing. So that's all I mean. All right, and again, like, you can see this on your calculator here. Let me just so you can see. I don't need to go all the way out to time is equal to infinity. All right, if I just take my E function, okay, negative here. Let's just go, whatever, 999. Okay, even at that, it's not actually 0. It's like, 0.0000. So many zeros, in fact, that your calculator doesn't even have storage registers, okay, to give you a value. Okay, so when you say after some amount of time, okay, the current that flows through it is equal to 0. Great. So then I have these two circuits here, okay, and these two circuits are supposed to be described by, okay, these two equations. This Q to T is equal to CV, 1 minus E to the negative T over RC, and I of T is equal to V times quantity E to the negative T over RC over R, all right? they've got V's in there, they've got C's in there, they've got R's in there. So which voltages, which resistance values, like what's going on here? Okay, so let's start with this one. All right, so remember, it's that time is equal to 0. Okay, what's the capacitor going to behave like? It's going to behave like a wire. Okay, it's just a pure conductive path. All right, now if I take and I apply Kirchhoff, okay, so I've got a single loop here. All right, this 12 volts, that's like my EMF. Okay, so that's my little epsilon thing. Okay, and I got 2 resistors. Actually, let me write these in black here, just so that they stand out against the loop. So that's my EMF. Okay, we'll call this one, that's my R1, that's my R2. Okay, and then this is my capacitor. There's going to be, if I write my KVL equation here, so KVL. Okay, just says the sum of the voltage rises and the drops has got to add up to 0. So I take my EMF, okay, and then if I go around my loop, so I'm starting right here. Okay, if I go around my loop, I start with the source, the 12-volt source. Okay, from that, I'm going to subtract, okay, I times R1. All right, and I'm just not going to bother with the subscript on the I because we have a series circuit, see, so all the current is constant in series. And then I have the capacitor, so let's call that VC, so some voltage across the capacitor. All right, minus I R2. Okay, well, my little trick says is that at time is equal to 0, there is no voltage drop across the capacitor. That's just equal to 0. Okay, so 0 is equal to epsilon minus I R1 minus I R2. And so what do we get here? Epsilon minus, I'm going to factor out an I from each of these and get R1 plus R2. Now look at this, it's kind of interesting. See, so if I move the I times R1 plus R2 over to the other side, I mean, this should look familiar. All right, we're really just looking at, see, like epsilon is voltage. So honestly, this is just Ohm's law. Okay, where this would be like the resistance in series. See, so when we introduce series circuits, we're supposed to add up the resistors, and we never really explain why. Well, it's because it's a consequence of applying Kirchhoff's voltage law. Okay, that's why that's the case. And in fact, this R here, okay, this is the R that shows up in our equations here. See, so let me make a copy of that and bring it down, sneak it in there. Okay, so for this case, okay, this R, that R right there, that's the R in these equations. It's kind of neat, isn't it? Okay, something else, what's the voltage? Okay, well, to get the voltage, we're going to have to look at kind of the end game here. So we'll come back to that in just a second. Okay, we got the R part. That's kind of the important piece. All right, so then let's go look at this. You've got to be conscious of this stuff because it's a little bit different circuit now. Okay, does that change the R that I use in my equations? Actually, yes, it does. Okay, so this is my EMF. Okay, and then I got these 2 resistors, so we'll call that one R1. We'll call that one R2. All right. The time is equal to 0. All right, the capacitor is going to act like a wire. See, so that's like it's just a straight conducting path that goes across. I guess I could do that over here too. So just think of it like a wire. Okay, well, the wire has no resistance. So what we have here is the current that comes out of the voltage source. Okay, it's got to pass through this 4 ohm resistor. It's got no choice, but once it gets to this junction, now it's got options. Okay, it can choose to go through a path of resistance or choose to go through a path of no resistance. It's all going to go through here, all of it. Okay, so we call this a short circuit. So we're shorting out R2. So we're providing a path, okay, for the current to flow. So if I draw my loop, okay, I'm just going to do another color just to contrast, all right, what I did on the other side. Okay, this is now my KVL loop. Okay, so I'm going to start here. Kirchhoff's voltage law says the sum of the voltage rises and drops has got to add up to 0. So there's my EMF. All right, I get this current that flows through R1, but then the rest of it's going to go through the capacitor. Okay, and sorry, my C's kind of messy there. Let me clean that up a little bit. Okay, at time is equal to 0, the capacitor acts like a wire, so there is no voltage drop here. All right, and what am I left with? 0 equals EMF minus I times R1. And so we just get this single resistor times the current is equal to the EMF. It's just Ohm's law again. All right, if I could put some numbers into this, okay? Let me scooch this down a little bit. Just kind of emphasize the point here. All right, so if I go back to this circuit here, okay, when I'm considering both R's, see, so I've got two R's, so I've got R plus R. I can figure out the current. So I got 4 plus 4, so each of the two resistors, and then the EMF is the 12 volts. So then I get I times 8 is equal to 12. So over here, the current is just going to be 1.5 amps. Okay, and that's important for us to figure out the current. What's more important, okay, is that R is equal to 8 ohms over here. Okay, so when we're applying, just charging a capacitor, it's 8 ohms, okay, that we need over here. On the other side, a little bit different. Okay, what's the current? Different circuit. All right, R1 is just 4 ohms. We can see it. The EMF is 12. So then we get 12 over 4 is 3 amps. So we get a higher current. Okay, but more importantly, okay, this R here, that R1, that's our R that we put in to these two charging capacitor equations. So put that over there, and oh geez, choosing green was probably the wrong color here. Let's make that red so that we can see this side over here. So this R, that's the 8 ohms. Okay, over here, this R, that's the 4 ohms. Okay, I think that's a little bit cleaner. All right, so then that's just initially. That's the first little trick, is we think of the capacitor initially as behaving, all right, like a wire. Okay, what about a long period of time? Okay, after a long period of time, the capacitor is going to act like an open. Okay, so now let's go look at after a long period of time. Same two circuits, okay? After a long period of time, the capacitor is going to act like an open. All right, so then long time. All right, so I snuck in a little, at least I thought I had a little box in here somewhere. There we go. Okay, so after a long time, it's just going to act like an open. So what? Well, if there is an open circuit, like we no longer have a complete path, okay, to flow. So no current flows. When we turn off the light switch, what we're doing is we're turning off the current. Okay, and why does that matter? Well, think about this for a second. Okay, so we have these two resistors, and we got this EMF. So let me label those again. So we made this one R1. Okay, we made this one R2. All right, well, if no current flows out of the EMF, well then, from Ohm's law, if we look at this resistor here, if my current is equal to 0, well, that also tells me that the voltage across this resistor is equal to 0. There is no voltage drop across the resistor. Okay, so I got this 12-volt source, so just think like, you know, over here we're at 12 volts, but if there's no voltage drop across this, over here we're at 12 volts. If there's no voltage drop, well then, this is just one continuous node, okay, place where there's no change in voltage. All right, and the same thing happens over here. If I consider this side, okay, Ohm's law says that, you know, the voltage drop across resistor number 2 is contingent on the current that's flowing through it. Well, if there's no current, then there's no voltage drop either. So then what we wind up with is the voltage everywhere along here is exactly the same. So what does that mean? It means that there's a potential difference. There's a voltage difference, okay, across that capacitor. See, like I put the little box there just to hide it, okay, but it's not like we took the capacitor out of the circuit. It's just behaving like an open, okay? There's still a voltage across it, all right? So if we connected up a voltmeter, what would it read? It would read 12 volts, okay? Or if I tried to apply Kirchhoff's voltage law now, all right, well, I've got the EMF, and I've got the voltage across the capacitor, and that's it. There's no current flowing through the circuit now, so all that tells me is that the voltage across the capacitor is equal to EMF at a very long time. I know it's a weird concept, okay, but that is, in fact, that is the way that it behaves. All right, so just remember, after a long period of time, there is a voltage across the capacitor, even though there's no current flowing through it. Just like if we bought a battery, okay, you know, we go buy a AA or AAA, it's 1.5 volts. That voltage difference is there whether or not we plug in the battery or not. Okay, that's pretty wild. Now, what about over here? Okay, after a long period of time, okay, again, the thing acts like an open. I wish I wouldn't have erased my little box here. I'll make another one. Okay, so just imagine, okay, after a long period of time, this is just going to behave, all right, like an open circuit. Okay, what does that mean? Well, that's a node, a single conductive path. See, so like everything along that green line is at the same voltage. Okay, if I go over here, here's another conductive path, that's the same voltage. Here's another conductive path, that's the same voltage. Okay, so point is, if I call this is my EMF. Okay, we call this one, just want to be consistent here. So this is, yeah, it's R1. Okay, so that's R1, and that's R2. Okay, well, there's going to be some voltage drop across this R2. So we go from the magenta down to the green. Well, that's also the voltage drop across the capacitor. And with this case, after a long period of time, see over here, no current flows at all because there's no path. This is acting like an open. Over here, there is a path for the current to flow. I can make a loop where there is current. So see if I do my KVL loop here. Oops, sorry. EMF, okay, minus some current through R1, minus some current through R2. Oh, I forgot to put the little 2 on there. Okay, and I got a complete loop. See, like I started here and I went all the way around. I got all my components. Okay, I got 2 resistors in parallel. See, so after a long time, okay, the behavior of the circuit is going to change. Go back to green here. Epsilon minus, so we got this I, we got these 2 resistors in series now, so we got R1 plus R2. Okay, look, our series rule shows up again, so I get I, R1 plus R2 is equal to our EMF. Okay, so then what's our current now? We've seen this before, so 4 plus 4 is equal to 12, so then that's 8, so then 12 over 8. So now, after a long time, we've got 1.5 amps flowing through this thing. Okay, so what? Well, if I know the current that's flowing through this, okay, well then I've got a series circuit here. So this is the current, so it flows out of the source, goes through R1, okay, also goes through R2 here. So then if I calculate the voltage drop across R2, so the voltage drop across R2 is just equal to the current times the resistor value for R2. So V2 is equal to that 1.5 amps times the resistor value is 4. So then 1.5 times 4, what is that? 6 volts. Okay, so this V2 here. All right, so like the voltage drop from here to here. Okay, that's the 6 volts. But, well, look, I got a magenta node and I got a green node. Okay, what's hiding behind here is the capacitor still there. Okay, and it's wired in parallel with this 4 ohm resistor. So in this case, if I was going to measure the voltage drop across here, that's still 6 volts. That's the voltage across my capacitor after a long time. See, so when I apply, where did I lost my equations? Okay, for this guy, okay, that resistor value from before, that's that 4 ohms from up above. Okay, so just bring that down so I don't forget. Okay, the voltage value over here. Okay, that's the voltage across that parallel branch. That's 6 volts. Okay, so a different application for this circuit. Okay, if I go back over here, the voltage across the capacitor is the EMF. So same thing, bring these guys down so that we've got the full picture here. Okay, over here, the resistor value, that was the 8 ohms, okay, that we determined above. Okay, over here, after a long time, we see what the voltage is across the capacitor that we need for the equation. That's the EMF. A little doopy thing up there. Okay, so 2 different scenarios, 2 different circuits gives us 2 different applications of these equations, specifically 2 different voltage values, 2 different resistor values too. And I guess I probably should make this, I'll leave this blue just so that to draw the distinction here. So underline that. Okay, and then the last little thing I want to show you is we call these RC circuits. Okay, so with these equations, kind of the commonality between the charging equation and the current equation with this is that you get this negative T over RC. Okay, this RC thing comes together like this. All right, now there's some importance to this that I at least want to hint at. Okay, so if I take a resistor, all right, a resistor is typically measured in ohms, okay, and a capacitor is measured in Faradays. Okay, both these units are really honorary units. Okay, so this is simplified from something more complicated. Okay, so ohm C, so if we take Ohm's law V equals IR, okay, well then really it's voltage over current is equal to resistance, which means that ohms are really equivalent to the units of voltage, which is a volt, divided by the units of current, which is an amp. Okay, and if I take that a step further now, okay, well, a volt, we know this, a volt is just a joule per coulomb. So then I have joule per coulomb and amp for a joule per coulomb, excuse me, an amp. All right, that's the flow of charge. That's coulombs per second. Okay, so then if I take that, we never divide by a fraction. We multiply by reciprocal. So joule per coulomb, okay, times, what would that be? That'd be seconds over coulomb. So then what does that get us? Okay, so many arrows. Okay, so they get joule times seconds over coulomb squared. Believe it or not, that's an ohm. Okay, and I could actually take this farther if I needed to, because, well, joules is newtons times meters, and newtons, that's far enough, okay? What about this farad thing? Okay, well, farad, we can break it down because we know that, well, capacitance is just charge for voltage, right? Okay, and so really we can break this one down too. So the units of charge is coulomb, all right, and the unit of voltage is volt. So farad is a coulomb per volt. Okay, coulomb is fundamental. I can't take that any farther, so I'm stuck with that. For volts is joules per coulomb. So again, don't divide by fractions, multiply by reciprocal. So coulombs times coulombs divided by joules. Okay, it gets me to what the coulomb squared per joule. Okay, and that right there, that's a farad. Okay, well, so what? Okay, why do I need this? Why are we doing this? Well, again, with these RC circuits, we call them RC circuits because you wind up having to multiply R and C together in these equations that we use to describe their behavior. So really what's happening is to do an RC circuit, okay, you're taking and you're multiplying an ohm times a farad, but what that really means is you're taking an ohm, which is a joule second per coulomb squared, times a farad, which is a coulomb squared per joule. Okay, and if we simplify this out, so you see the joules cancel, the coulomb squared cancel, and we're left with this. All right, so resistance times capacitance is really something that's measured in seconds. Okay, so for whatever reason, when we multiply a resistor times a capacitor, we get a value, okay, that's a time. Okay, and as a result of this, okay, for a given resistor capacitor combination in a circuit, whether it's one resistor or multiple, if we get the R right, okay, we put it with the C, which is also a constant value, put those things together, okay, and we get a time. Okay, so they give it a special letter, they call it tau, okay, and they call this the time constant for a circuit. Okay, what the heck does that mean? Well, that's a story for a different video because this one's already gotten pretty long. Okay, so I'll leave you with that to think about. All right, so this is Mr. Zizek saying thanks for watching, and I'll see you next time.